In the previous lectures, we've learned how to summarize the data and how to compute its center or location or central value. Now we're going to consider something related but a bit different. We're going to consider the spread of the data, that is, how far does it seem to be away from its central value. To begin, let's consider again that data about the life expectancies of 197 different countries and territories. We already computed some things about this data. In particular, we learned that the median life expectancy is equal to 73.2 years. It's also not hard to compute that the mean life expectancy is equal to 69.9 years. So these are two different measures of the location or the central value of the data. But now we say, what about the spread of the data? How far does it seem to be away from these central values? Now, one way to think about this is to consider the data's box plot, which we saw already and which is shown here. The box plot shows us various summary statistics, the minimum and the first quartile and the median and the third quartile and the maximum. So the simplest way to think about the spread of the data is to look at its range, that is, just take the maximum value minus the minimum value. In this case, the range is equal to 83.4 years minus 47.8 years, which is equal to 35.6 years. So this tells us that all of the data can fit into an interval which is of length 35.6 years. Another thing we can do is look at the interquartile range, or IQR, as we've seen previously. The interquartile range is found by taking the third quartile minus the first quartile. In this case, it's equal to 76.7 years minus 64.7 years, which is equal to 12.0 years. So we can also say that for this data, the interquartile range is equal to 12.0 years. This means that the middle half of the data can fit into an interval which is of length 12.0 years. So now we can summarize the spread of the data either by the range or by the interquartile range, and those are both nice ways to summarize the spread. But they don't take into account all of the data values. They just take into account certain summary values. What if we wanted to use all of the deviations of all of the data values from their mean? Well, we could just try adding up all of the deviations of all of the values from their mean. But that would always add up to 0 because the positive deviations would exactly cancel the negative deviations. We could also try adding up the absolute values of all of the deviations of all of the data values. That would make sense, but it would be very hard to work with. It turns out what's the best and most useful thing to do is to add up the squares of all of the deviations of all of the data values from their means. Now in the end, we don't really want the sum, we want a sort of an average. So it turns out we'll want to divide this by n minus 1, by one less than the total number of data values. That gives us a formula for the variance of the data. Finally, if we want to undo all those squares that we did, we can take a big giant square root. So once we take a square root of 1 over n minus 1 times the sum of the squares of all the deviations from the mean value, that gives us what's called the standard deviation. It's a bit complicated, but it turns out to be a very important measure of the spread of some data. Now you may be wondering, why did we divide by n minus 1 instead of just dividing by n and taking an ordinary average? Well, it turns out that dividing by n minus 1 is the best thing to do. In fancy language, it gives us an unbiased estimator of the population variance. All we need to know is it's a smart thing to do. Intuitively, we can think that the first value doesn't tell us anything about the spread. It's only the remaining n minus 1 values which say something about the spread, and that turns out to be sort of why we need to divide by n minus 1. In any case, Often n will be large, and then it doesn't really matter if you divide by n or by n minus 1. So now we understand how to take not just the range and the interquartile range, but also the variance and thus the standard deviation of some data to figure out their spread. Now let's try working out an example by hand. Let's go back to those 9 student grades that we saw earlier. We already know in this case how to identify the minimum and the first quartile and the median and the third quartile and the maximum grade. This means right away we can compute the range by taking the maximum value minus the minimum value. We can also compute the interquartile range by taking the third quartile minus the first quartile. What about the variance and the standard deviation? Well, for starters, we have to compute the mean by adding up all 9 of those numbers and dividing them by 9, which is the total number of numbers. That gives us the mean value. Then we have to add up the squares of all the deviations from this mean value, divide it by 8, which is the number of numbers minus 1. That gives us the variance. And then finally, we need to take a square root in order to get the standard deviation. So in this case, in addition to saying that the range of the grades is 25 and that the interquartile range is 14, we can also say that the standard deviation is equal to 9.3. We'll be working more with these different measures of spread as we go along. For now, let's consider one last example. Let's consider again those salaries of the soccer players on the 2012 New York Red Bulls soccer team. We already computed that the median of these salaries is about $112,000, and the mean is about $518,000, which is a lot higher. We also considered trimming the data and said that if we eliminated the 2 highest and the 2 lowest salaries, then the median would stay exactly the same, but the mean would be a lot less, now just about $128,000. Let's stick with this example and see what it tells us about measures of spread. Here's a chart which shows for both the original data and the trim data various quantities. We can see that the range changes tremendously from over $5 million with the untrimmed data to just $268,000 with the trim data. One thing we can consider is whether that measure is robust or resistant to outliers. Certainly the answer is no, because the range changes tremendously if we remove a few outlier values. The interquartile range, on the other hand, is rather different. It's $150,000 for the full data and $146,000 for the trim data, almost the same. So we can say it is resistant to outliers. It is robust. Finally, we can consider the standard deviation that we just learned how to compute, and it's kind of complicated. We can also see that for the original data, the standard deviation is well over $1 million, but for the trim data, it's only $84,000. This says that the standard deviation is also not robust or not insensitive to outliers. So where does that leave us? We've now introduced 3 different ways of measuring the spread of data. First, we have the range, which is just the maximum value minus the minimum value. It's quite simple and often quite useful, but it's also not robust, and it's very sensitive to outliers or extremely large or small values. We also have the interquartile range, which is much more robust and in some ways a better way to measure the spread of data. Finally, we have the standard deviation, which is not robust to outliers, and it's quite complicated to compute, and yet it's going to turn out that that will be an extremely useful measure of spread for us. So there you have it, 3 different ways to measure the spread of data.